In this video, we'll be looking at compound interest and depreciation, which is how percentages can be used to calculate the growth or decay of something over time. Before you start this video, I'd recommend that you've watched the videos on both percentages and indices, as these processes will both be used during this video. Compound interest and depreciation is the process through which we can calculate the growth or the decay of an amount over time. It's used in order to take into account the concept that growth and decay is continual, but it must consider prior changes to the amount in question. In my lessons on this subject, I try to stress to my students how this process reveals the interest that you're going to pay on loans and credit cards, how your car will go down in value and your house or flat could go up. Understanding this concept is one of the keys to having some control over your finances for the rest of your adult life. Here is the formula for growth or decay. We start with the initial amount, which is sometimes called the capital or initial investment, if we're referring to money. Next, we have the multiplier, which is dependent on whether something is growing or decaying. If there is growth, as in compound interest, we'll take the 100% of the initial amount and we're going to add the percentage growth. For instance, a 5% increase would be 100% plus 5% to give 105%, or 1.05 as a decimal. We tend to convert the multiplier to a decimal to save any confusion between a percentage symbol and a power. If something's reducing in size or decaying, we would calculate the multiplier by subtracting it from the 100%. For instance, 12% decrease, the multiplier would be 100%, take away 12% to give you 88%, or 0.88 as a decimal. As this is smaller than 100%, or 1, anything being multiplied by it would be made smaller as a result. In both cases, growth and decay, the effect of the multiplier changes over time, the total amount of which we referred to as the term. I'll show you how to use that and why we can use it as the power of the multiplier. In this question, Sue invests £2,100 in a bank for 6 years, where it earns 4% compound interest each year. We're asked to calculate the total amount Sue has in the bank at the end of the 6 years. We're then asked to compare this to a simple interest at the same rate. Most financial institutions will only use the compound interest model in order to calculate this. But often, in GCSE, we're asked to compare the two different models of growth. Firstly, we want to create the multiplier. As it's an interest question, we're going to add the 4% to 100%, which is 104%, or 1.04 as a decimal. We can then calculate the first year by multiplying 2,100 by 1.04 to get the total at the end of the first year. As we then multiply that result by 1.04 for the second, and so on, we could write it as follows. 2,100 times 1.04, 1.04, 1.04, 1.04, 1.04, and 1.04. As we're multiplying by 6 1.04s, we can write it as 1.04 to the power of 6 to save space and confusion. This is the reason that we can use the term or time period as the power. And it gives us 2,100 times 1.04 to the power of 6, which equals £2,657.17. This is the amount she has in the account at the end of 6 years. We're now asked to compare that to a simple interest model. In simple interest, you calculate the interest of the initial investment or amount, and then that is received each year. So we're going to calculate that as finding 4% of 2,100, which is £84. We'll times that by 6 to give us £504, and then add that to the initial amount or the initial investment to get £2,604. If we then subtract that from £2,657.17, we get the difference of £53.17. This is how much more you get from the compound interest model. In this problem, we have a car which decreases in value by 14% each year. This is called depreciation. If Tina bought the car 3 years ago for £15,000, what would be its value today? Firstly, let's calculate the multiplier by subtracting 14 from 100%. Which is going to equal 86% or 0.86. Then we can multiply that as follows. 15,000 times 0.86 times 0.86 times 0.86, or 15,000 times 0.86 to the power of 3, which equals £9,540 and 84 pence. This is the value of the car after the 3 years. As you can imagine, this depreciation has a greater effect when the car is newer and more expensive, as the percentage decrease is of a larger amount. As the years progress, the rate will stay the same but have less of an effect. In the next question, we're asked to calculate the height of a tree after a period of growth. It states that the height of the tree will increase by 15% each year. When planted, the tree was 110 centimetres tall, and we're asked how tall it will be in metres after 10 years, to 1 decimal place. Note the change in the unit of measurement. Firstly, let's work out the multiplier, which is going to be 100% plus 15%, or 115%, 1.15, as it's a growth. Let's apply that to the original amount of 110, using the term as the power. So 110 times 1.15 to the power of 10 is going to give us 445.011 and ongoing. As that is in centimetres, let's divide it by 100 to get 4.45, or 4.5 to 1 decimal place. So after 10 years, we're predicting it will grow to 4.5 metres tall. On this next question, we've got a full water tank which holds 1,500 litres of water. It begins to leak water at the rate of 12% of its contents per hour. We're asked to calculate how much water is left in the tank after 6 hours. Let's work out the multiplier by doing 100% minus 12%, which gives us 88%, or 0.88. We can then apply this to the initial amount of 1,500, using the term as the power. The term here is going to be in hours rather than years in the previous examples. So 1,500 times 0.88 to the power of 6 is going to equal 696.61 litres. So we've calculated there will be 696.61 litres left after 6 hours. In this question, we have a ball that's dropped, bounces, and then rises to 85% of the previous height from which it was dropped. The ball is initially dropped from the height of 5 metres, and we're asked to calculate the height of the rise after the first bounce, and then after the second bounce. In order to solve this, we need to recognise that we're going to be using depreciation or a decay model to calculate the height after each bounce. To calculate A, we want to do 5 times 0.85, which gives us 4.25 metres after the first bounce. Then to calculate B, we should recognise that the term is the number of bounces. So 5 times 0.85 to the power of 2 gives you 3.61 metres after the second bounce. We're now asked to calculate the number of bounces that will continue to rise to over 2 metres. We can find this by increasing the term or the number of bounces until we discover the bounce that doesn't exceed this height. So 5 times 0.85 to the power of 3 will give 3.07 metres. To the power of 4 will give 2.61 metres. To the power of 5, 2.22 metres. And to the power of 6, 1.88 metres. This is the first bounce that does not return the ball to over 2 metres, so we can say it will continue to rise to over 2 metres for 5 bounces. Through this video, we looked at how to calculate compound interest and depreciation by using a multiplier method, and why we can use the term length as the power for the multiplier. In the next video, we'll be looking at conversion graphs and the gradient. I'll see you then.